Hi, I'm Ray Dean. Today, I'm honored to present RDPro Scalable Monitoring with Sufficient Coverage in Complex Data Center Networks. This work was jointly done at Peking University and Huawei. My professor Xun Huang is a corresponding author. Data center network monitoring is indispensable to providing reliable cloud services. Given modern scales of the data center infrastructure, failures are the norm rather than the exception. Here are some major failures in the region in Huawei Cloud in the past 18 months. They dragged down quality of service for tens of thousands of users. Moreover, they took 10 hours on average to repair and had diverse root causes like port flapping, state mismatch, chip errors, and card errors. A natural question to ask is, why these failures took so long to repair? Let's delve into one such case where one of the 8 aggregated ports flapped about every 30 seconds. In this scenario, we had 8 member ports on each of the 2 peer switches. They were connected by 8 physical links. We configured on both switches to bundle these links into a link aggregation group, or LAG in short, so that they collectively function as a layer 3 interface. The forwarding rule in the LAG is briefly 2 steps. First, the IP routing table decides a packet should go through this LAG interface. Then, a proprietary layer 2 hash selects one port in the LAG to forward the packet. We had 12 probe tasks via this LAG interface, where each task injected synthetic traffic between hosts and traced metrics like round-trip times and loss rates. Each task could exercise one of the many types of pings and so on. However, none of them went through the flat port. A quick calculation showed that this could happen with more than 20% probability, which was not rare. Thus, we covered these layer 3 interfaces, but not all of the layer 2 ports. Meanwhile, all of our deployed tools didn't raise any alarms, including NetFlow, SNMP, syslog, BGP monitoring protocol, and ERSpan. We finally resolved this issue by isolating and restarting the buggy port. After studying all these failures, we find the common culprit is the insufficient layer 2 coverage, since all of them occur on uncovered layer 2 ports. Thus, with respect to coverage granularity, we favor layer 2 over 3. Layer 3 coverage means we only ensure every layer 3 interface has some task going through it. It is not good enough since the interface can be a bundle of layer 2 ports, where each port has its own working status. Even if a layer 3 interface looks good to quite a lot of tasks, some of its member ports can still be degraded. Next, as per sufficient coverage, we find 99% is a satisfying threshold, and the strict requirement of 100% coverage is unnecessary. 100% means all ports are covered. It has 2 drawbacks. First, the resource overhead is overly high in complex data centers, as we will shortly see. Second, the benefit gained from 99 to 100% is only marginal. In fact, a coverage higher than 99% significantly improved the accuracy of failure detection. To illustrate, we inject simulated random drops into a closed network containing 10,000 switches. We fix the detection algorithm and vary the set of probe tasks to achieve different coverage levels. When the coverage rises from 97 to 99%, the false positive ratio reduces from 4% to nearly 0, and the false negative ratio reduces from 10% to only 3%. Similar trends are also observed in detection of other types of failures, like congestion-related packet drops. Now is the time to introduce the formal definition of layer 2 coverage. We'll express it in 2 variables, alpha and p. Alpha indicates the intended number of tasks through each port, whose typical value is between 1 and 5. P is the portion of layer 2 ports that have least alpha tasks through it. Then, sufficient coverage implies P is no less than 99% for an operator-specified alpha. We let alpha and P be the input of our system, and our task is to generate tasks fulfilling alpha P coverage. A good question here is why we don't maximize P. A brief answer is that Theoretically, P can be infinitely close to 1 if you add tons of tasks. However, this leads to high overhead and marginal gain. We identified two challenges concerning sufficient layer 2 coverage. The first one is complexity. Many deploy techniques blur the view of layer 2 ports and drive the path control on layer 2 invisible. For example, in Huawei Cloud's data centers, there are 4 such techniques that are deeply connected to each other, namely link aggregation, switch stacking, virtual routing and forwarding, and equal cost multipath routing. What's worse, switch vendors mostly do not disclose detailed layer 2 metrics due to reasons like proprietary and security concerns, maintenance burden, and potential speed slowdown. Most metrics are up to layer 3. The second challenge is scalability. As probing is resource constrained, it is desirable to keep the probe planning time within a few minutes in order to respond to network changes promptly. Moreover, we must ensure server exercises no more than a few hundreds of tasks due to the tight CPU and NIC budget available to it. Sadly, our old PMH-like monitoring method can't address this challenge. Specifically, it achieved an estimated coverage of around 80%, far from being sufficient. Although it has low planning time due to its full mesh probing, it produces a prohibitively high probe volume. For example, if you want to improve its coverage by slightly increasing task numbers, then some servers are likely to be overloaded. Unfortunately, existing solutions fall short of addressing these challenges. We classify them into 3 categories. The first category treats switches as black boxes. This includes methods for network tomography and full mesh probing. Traditionally, they focus on layer 3 coverage, and lowering to layer 2 is non-trivial. They also have scalability issues since the optimal planning is NP-hard. In fact, they usually sacrifice either time or volume to satisfy the other. The second category treats switches as white boxes. This includes methods like packet sampling, in-network telemetry, and measurements. Promising as they are, their power is limited by built-in capabilities on hardware. They can be intrusive and even incompatible with existing devices. Nonetheless, they are good complements and can be used in combination with our system for better performance. The last category is network verification. We already use config verification tools like Batfish in Huawei Cloud. Note that they focus on verifying static properties by analyzing a snapshot of the network. Instead, we aim at continuous monitoring. To this end, our contribution is a new monitoring system, RDProbe. It's fully aware of complexity in production environments and is guaranteed to achieve sufficient coverage. It's also designed to achieve high scalability and fault tolerance. Finally, it has large-scale deployment in 3 production regions. Now we take a look at RDProbe's architecture. It has 5 steps in an epoch, which usually lasts for 3 minutes. It begins with topology construction, which aims to tackle the complexity challenge. To do so, it reveals all layer 2 ports and their mutual reachability by transforming a layer 3 topology. The resulted topology, which we call the de facto one, can be different from that on layer 2 or 3. Next, we come to the kernel of RDProbe, namely two-phase generation. It ensures sufficient coverage while addressing the scalability challenge in 2 phases. Phase 1 is randomized generation. Its high-level idea is that we can randomly select tasks with arbitrary sources and destinations so that most ports are evenly and sufficiently covered. Then, Phase 2, also known as deterministic generation, will complement Phase 1 to reach the prescribed coverage requirement. It will produce additional tasks through the yet undercovered ports. To summarize, by combining randomized and deterministic methods, we can realize better planning time and probe volume simultaneously. 2 additional steps come between Phase 1 and 2 to compute coverage statistics. The first is package mirroring, which mirrors probe packets to the control plan for a region. Then goes coverage computation. It listens for mirror packets and compute layer 3 coverage. These statistics will guide phase 2 in locating undercover ports. Having seen the overall architecture, let's delve into a bit details. Recall that topology construction incrementally modifies layer 3 topology into a de facto one. The key idea is that we can parse related switch configurations into equivalent graph operations. Here is a minimal example. Assume we have topology on the left. Then the configuration for this lag will look like this piece of text. And we know 2 GB Ethernet ports are its member ports. In layer 3 topo, we have only one logical link representing this connection. So we issue a split edge operation, and this edge will become 2 physical links in the de facto topology. Note that one configuration can translate to multiple operations, and we encourage you to read our paper for more complex examples. Also, concrete details of topology construction are up to the data centers themselves. We show how it's designed in Huawei Cloud. Now we are ready for phase 1, where we have coverage requirement and de facto topology at hand. To produce phase 1 tasks, we randomly select tasks for an even coverage. Assume we need T tasks and have A healthy servers. Then each server randomly selects T over A destination servers for load balance. So the crux here is, how can we know T? Here's the insight. We can model phase 1 using the coupon collector theory. It allows us to relate T and the achieved P for any given alpha. Assume there are S switches in the network and the larger switch has M ports. We have 3 key results. First, we can efficiently determine the value of T. Next, our T will not be much larger than the optimal volume, which is NP hard to find. Finally, a vast majority of ports are sufficiently covered in phase 1. Now we discuss phase 2, where we've got our layer 3 coverage counters. The idea is to first locate undercovered interfaces so far, and then find additional tasks, go through them. So, how to locate undercovered interface? Well, we again use coupon collector theory to find how many tasks are required per layer 3 interface. Those whose coverage counters are below the required values are our targets. Then, how to find additional tasks through it? It turns out that we use BFS to find the nearest neighbors. Moreover, to ensure that the newly added tasks go through the interface, we exercise FP in IP ping for path control. Finally, why we don't use phase 2 from scratch due to 2 reasons. One is that it's only effective after most ports are covered. Second, it cannot exercise other protocols beyond IP and IP ping. Now we show the deployment results. All the 3 deployed regions have around 1,000 switches and tens of thousands of links. Not only does RDPro guarantee sufficient layer 2 coverage, it also improves coverage with fewer tasks. We also case study how RDPro helps detect new failures and tolerate numerous faults in the paper. We further conduct large-scale simulation on NF3 using 2 popular topologies. Their scales are an order higher than the deployed regions. Besides sufficient coverage, we find it shows good scalability. For example, the volume is about switch number to the power of 1.53. The optimal power we can expect is 1.5, so it is only 300th larger. Besides, the planning time is strictly within 1 minute at the larger scales. Compared with previous industrial solutions, including PingMesh, NetBouncer, and Detector, we find that RDPro is the only one achieving sufficient coverage and scalability at the same time. To conclude, we first discovered the fact that sufficient layer 2 coverage matters and suffices. Then, the challenges of complexity and scalability make it hard to achieve. We tackle complexity by topology construction and scalability by two-phase generation. Last but not least, RE-Pro is designed to be an industry-grade solution and demonstrate thought-out performance. Thank you for listening, and I'd love to take any questions.